But we should probably get. Yep.
Hi, everyone. Today, we are going to start with the closing event for today. So it's my great pleasure to introduce Microsoft Computational Pathology Workshop. So please, the floor is yours.
Thank you. Good afternoon. My name is Anton. I'm a principal software engineer at Microsoft, and I'd like to mostly talk about the full set of open source tools that we have released over the last couple of years in the area of biomedical imaging. I'm going to start out by giving a rough overview of what our team is really doing, give you an overview of the many open source tools that we have, and then I'm going to zoom in on to multimodal learning for chest X-rays and radiological reports, and then zoom in further, moving on to actual pathology, where I'll then also hand over to my colleague Valentina. So in terms of our team, we're working on radiology, more specifically on chest X-rays and on computational pathology. So for both of these areas, we have been focusing in particular on multimodal learning. And for us, that means images plus associated text. So pathology or radiological reports. And we're trying to build out these models as foundational models that ideally can be transferred over to other domains. And we're trying to open source pretty much all of our core components. So not just publications, but also the model building and evaluation workflows that we're using on a day-to-day basis. And for us, this is also a way how we engage with clinical and commercial partners, where we build open source tools with them and for them. So I've tried to bring a little bit of order into this large zoo of tools that we have by grouping them along two major axes. First one being the application area. So we've been working for many years already on 3D segmentation. We're working on computational pathology and radiology. All of the many tools to do with 3D segmentation live in GitHub repositories that are prefixed in RAI, and pathology and radiology live in GitHub repository hi-ml or short hi-ml in different subfolders. So we're really proud that we have been able to go through a full process of clinical validation with our 3D segmentation models, in particular for prostate and head and neck cancer. And I'm going to talk more about that in a bit. We have full model training workflows, detailed reports generated, and in particular for pathology and radiology, we found it super useful to work with self-supervised learning. So that allowed us to tap into the vast pools of unlabeled data that is available. Again, this has really pushed our modeling capabilities forward. We have also open sourced model configurations for many known public data sets for all three areas. Pre-trained models are also available for some of these data sets, as long as the licensing terms, of course, permit. In particular, for radiology, we have released a large number of models that I'm going to talk about later. Everything is available via Hugging Face. And most recently, we've also released a pre-trained model for hippocampal segmentation. The one thing where 3D segmentation still stands out from our other application areas is that we have been able to build and open source a full set of tools that allow you to put an AI model into a clinical context and evaluate it as part of a real clinical workflow. And more about that in the next slides, because I'm now going to focus specifically on 3D segmentation for the next couple of minutes. Oops. Here we go. Just a quick recap of how a clinical workflow for using medical imaging would typically look like. So you have a CT scanner here. The acquired image gets sent over to the hospital's image store, the PACS system. And this all happens via the so-called DICOM network. And we've open sourced the inner gateway, which is effectively a DICOM listener that sits inside of the hospital boundaries and can, for example, pick up a pelvic CT scan. And it can be configured to now take this pelvic CT scan, strip off all sensitive information, all personal identifiable information, and send it up to the cloud, to the INRA inference service. From there on, the scan goes to Azure Machine Learning, where the actual segmentation happens. The segmentation results gets then sent back to the inference service and further on to the gateway, which reattaches all of the stripped out information, and the image gets sent back into the PACS system. And from here on, the clinicians are again on their home turf in a way, because they can now inspect the segmentation with all of the typical clinical tools. They can make corrections, and if they're fine with the segmentation results, just send it straight on to the treatment planning software. If it's really urgent, yes, but otherwise I would rather if you could hold on to the end, if that's okay. Right. We've been going through a clinical validation process with our colleagues here at Edinburgh's Hospital in Cambridge. So we've built prostate segmentation model and a head and neck cancer segmentation model with them. And the evaluation of these models really integrated into the clinical workflow showed that it leads to really a drastic improvement in terms of workflow time. So it shortens the overall treatment process by a pretty significant factor. And this is really ultimately the metric that clinicians care about. It's about how it impacts their workflow rather than how it performs in terms of DICE score. Edinburgh's Hospital have then, as a result of this work, been given a grant from NHSX to further develop these tools and roll them out across multiple hospitals here in the UK. More generally, these open source deployment tools can work with pretty much anything that is happening in the clinical DICOM network. So it's not just limited to 3D segmentation. This is, I think, the key message that I wanted to bring across. If we want to have a play with that, we have also released one pre-trained segmentation model for segmenting the hippocampus based on the ADNI open source dataset. Now, let's move on. Let's zoom in more towards radiology and the work that we've been recently doing in this space. So multimodal learning for us in this context means looking at images plus text. So chest X-rays plus radiological reports, or whole slide images and pathology reports. And we want to build foundation models that transfer over to multiple application domains, ideally. For radiology, our raw data looks like this. We have a chest X-ray, the usual thing. We have a radiological report and nothing else. And we'd now like to learn from that in a purely self-supervised manner. So we want to learn meaningful representations for both the text and the image. And most importantly, we want to do that we want to learn local embeddings. So embeddings that also capture small parts of the image so that we can afterwards do a more detailed matching of where the text is similar to a part of the image. So let me show you how we managed to do that. And this is part of a work that will be published later this year at ECCV. On the image side, we take the chest X-ray image. We break it down into small 16 by 16 pixel blocks and feed it through an image encoder. Then further on through a projection layer, which gives us then the final latent space for each of the small blocks. Then we do pooling to get to the full image embedding. There is a lot more happening here on the text side. So on the text side, we've had to build pretty much a customized model that understands the language for radiological reports. First of all, because of the hugely different vocabulary. So this CXR BERT model, as we've called it, understands words like cardiomegaly that a normal language model would just split up into subtokens, and then it's not really helpful anymore. There's a lot more fine-tuning happening on the language side that I can't really talk about here, so please do have a look at this paper. We get the CLS token out, we again project it, and then get a text embedding as well. We take the text embedding and the image embedding, feed it into a symmetric contrastive loss function, and then let the model learn. Now, how can we use that for inference? Well, we can now take, for example, a text prompt, feed it through the text encoding part, and get the text embedding vector. And now we can actually compare this text embedding vector to each of the local embedding vectors of small part of the image and reduce for a downstream task to effectively an image to text similarity task. An example notebook for that is also open sourced in our repository. So you feed in a text prompt, you feed in an image, and you get back a heat map effectively of text to image similarity. Example coming here up on the next slide. So this image comes from the MIMIC CXR dataset. This query here, cardiac silhouette is enlarged, comes from the associated report. Now we can query this model, and it's going to say that this text is most similar to the image here in this region. How do we assess whether this is good? Well, we've effectively created a new benchmark dataset, a phrase grounding benchmark dataset, and open source that as well, where 2 board certified radiologists have actually looked at these image and text pairs and drawn bounding boxes around that. And we see indeed that there is a pretty good overlap from the model activation area to where the bounding box here is. Okay, in the interest of time, I think I'm going to speed up a little bit here. You can do that, of course, for more queries. I want to highlight here also that the model has learned a pretty good sense of direction here. If we query the model for whether there are any left lobe opacities, we get a rather weak response. If we query it for are there any right lobe opacities, then the model does fire quite a bit more. And I want to highlight again that this all has been learned purely based, so without any ground truth annotations that link text to parts of the image. That's really the amazing capability of this model. We can also, just for the fun of it, we can also see whether the model responds in some way to text that does not indicate any pathology here. And indeed, we do get a rather low response here. Linking back to the topic of open source assets, the trained language model for with the radiology vocabulary is available on Hugging Face, ready for reuse. And if you're working in this area, you might also want to look at this MSCXR datasets that's phrase grounding. So where radiologists have drawn bounding boxes on the images to highlight specific pathologies on a total of, I think, 1,100 images. The full trained image embedding model is also available on Hugging Face. So of course, how do we now make the transition over to histopathology? And we're still figuring that one out. We know that we've now something that is pretty powerful, a model that is pretty powerful to do self-supervised learning for radiology. When we now look at pathology, there are a lot of challenges coming up. Of course, the first obvious one is the images are huge. The reports have a different structure. And we are, to some degree, held back by a lack of really good data sets in this space. That's also one of our problems at the moment. More about pathology from my colleague Valentina in a couple of minutes. Wanted to point you to a couple of these links here where we have collected information both about our INRI open source tools, everything that is available in the HiML repository, and generally also our work on self-supervised learning for the radiology domain. And with that, I'd love to thank you for your attention and happy to take any questions.
Yeah. So sorry, for clarity purposes, yes, the workshop is taking questions. So if you want to
over to you.
Yeah.
So my question was actually in relation to one of the very first slides that you showed, where you're taking data images, de-identifying them, then taking them over to the right-hand side for analysis, and then bringing the analysis results back through the firewall. Right? Yeah, this one. Yeah. So my question was going to be, how do you relate the results of the de-identified images back to the clinical records for a patient, where obviously you have all the identifiers, NHS numbers, and so on?
Yeah. The INRI gateway here, this is still within the hospital trust boundaries. So it can keep, for example, a series instance UID that we are not going to strip off, because we think that this is something that will probably not be able to trace back to any identifiable information. And with the series instance UID, we can now link back the segmentation result coming from here to the actual information that we stripped off beforehand.
So you generate some sort of hash and you keep the hash table on the left-hand side.
Exactly.
Okay, great. Thank you.
We have time for one quick question.
Yeah, I was just going to ask, you see how there's the word embedding and the image embedding trying to contrast with loss. Now, I'm not a clinician, but my question is, how does that generalize to different sort of vocabulary? And if it's trained contrastively, if I try and say it's an X-ray of something else, like not lungs or chest X-ray, or maybe it's, I don't know, maybe the vocabulary changed in some way, would I not be able to replace the embedding model with a slightly modified one, because it would affect the whole way the network was trained? Because I'm trying to see how that would like, what's the generalizability here, especially like histopathology, if you're trying to extend it to that?
We would probably have to build a customized model for the language that is used in the pathology reports as well. Absolutely. And there are quite a few tweaks here in this type of model that makes it really understand also the different sections of a radiologist report. Like it has a special understanding of the impression section and of the findings section, for example, that are also used during the training of this model. So this is quite involved. I would really like to point you to the preprint that describes this in all of its gory details. But just want to highlight here that working with a very carefully tuned language model has really made pretty much all of the difference. Is it fair to say that, Ozan? Yes, please. Yeah.
So you also released the canonical model in the same page. So that model was actually trained with abstracts. So outside the chest, outside the chest radiological. So you might expect like some understanding of general radiological domain and beyond that to be captured by this model. Like the canonical model that you define things are for chest radiology, so we really work with that. But if your application is outside the chest radiology domain, you may still want to use that model. So that might be kind of like a part of the different ways of phrasing you want to for like
Okay.
So that model might be suitable for application. And I think the future research would be interested in expanding the model for different platforms.
Okay, thank you.
Thank you. We need to move to the next talk. Thank you very much.
Hello, everyone. I'm Valentina, Senior Applied Researcher in the Biomedical Imaging team. I hope you still have some energy to listen to the last two talks of the day. In this talk, I'm going to present about the tools we developed for machine learning research in computational pathology. And this is everything is open source, and we hope it can be useful also to other researchers in the room. And we want to hear feedback about it. For everyone that has ever tried to develop a machine learning model for computational pathology, but probably also other fields, you probably know that there is much more to handle than just deciding which is the best machine learning architecture to use for the downstream task. In our experience, the first thing is collecting data and storing this data in a place where it can be easily accessible and consumed by a machine learning model. In our case, in our workflow, what we use is Azure Blob Storage. And usually after there is a phase where we are interested in looking at this data to understand what we're dealing with and for some quality control. And our tool at the moment is the Digital Slide Archive. That is another open source tool that we integrated in our workflow. And once we are convinced about the data, we usually consume the pathology slides for training a machine learning experiment. Our way to do it is on the cloud using Azure Machine Learning Service. And we usually obtain some results. And at that point, we're interested in looking at the results, looking at some visualizations, understanding what this model is really learning, what it's paying attention to. Does that make sense for a clinician, for example? And all this workflow that we developed, I think it's really suitable for iteration and experimentation, and particularly it's useful for having a very collaborative and interdisciplinary work. We work with machine learning scientists, engineers, clinicians, and particularly it's important to, for example, be able to share with the clinicians the data and the results that we have and getting their feedback. And I want to stress that this package that is open source can actually be used also outside Azure, as long as you have a machine with enough GPUs, you can use it. And I would say the biggest advantages of making use of this package that is called IML, this is what Anton was presenting before, is first of all having a well-tested and reproducible code base. And the other thing is, like, when we started to operate in this field, we realized that it was very difficult to reproduce some papers. Often there was not enough open source code. The data was not always completely open source. So we spent quite a lot of time in trying to develop some benchmark models that we open sourced. And if you follow the documentation that we have with the package, you should be able to reproduce exactly some results in the literature that we share. Particularly, there are two use cases. I will speak about it just in a minute. And in case you're running also this package on Azure, you gain something more because in that case, there is flexible access to GPUs. Usually, these machine learning models for computational pathologies really computationally expensive, and it's convenient to have elastic resources. And it means you can share data across teams without duplicating. And that means also you're sure you're really running on the same data, and you gain in traceability of your experiments. So let me tell you about the 2 use cases we focus on in our team in the past few months. The first one is detecting genetic mutation from H&E slides. And in this case, the benchmark model that we developed is based on the TCGA-CRCK dataset that is freely available. This is a colorectal cancer dataset. And in particular, there are labels available for microsatellites, stability and instability. That is a genetic mutation. And we are able to reproduce the Deep Smile paper that has been released in this field for a genetic mutation. And the other use case is automatic tumor grading. In this case, the dataset that we used is the PANDA dataset. This is a dataset for prostate cancer that has been released for a Kaggle challenge 2 or 3 years ago. It contains more than 11,000 of slides, and it contains the Gleason grading that allows us to develop a pipeline for multi-class classification. So I described at the very beginning what was the full machine learning workflow. Let me now tell you more about the machine learning part of it. The type of pipeline that we support at the moment is a D-mill pipeline. This because for what we have seen also in the literature, it has been the most common approach in the past few years, and it has been pretty successful, especially for classification. That is the 2 tasks I presented before. Here you can see the different steps that are needed to obtain the classification. And we really made an effort in the code to make everything very modular so that the user can decide about different steps in a modular way without having to touch too much part of the code. Ideally, you should be able to just change a configuration file and be able to play with all these different options. And I'll describe in a moment like each of these steps in more detail, but at high level, usually there is a tiling part. The slides images are huge. We're not able to process them through a machine learning model altogether. So usually they are fraction in tiles. And after we're interested in learning features for each of the tile, and this requires having an encoder. Now, one possibility is to take a pre-trained encoder like ImageNet, but we have seen that natural images are really different from pathology images. That means it's convenient to actually train your own encoder, possibly on the same data set, if that is large enough, or at least on an histopathology data set that is much closer to the pathology images you want to work with. And for this, we developed a module for training your own self-supervised contrastive learning encoder that you can train and checkpoint and reuse the rest of the pipeline. Once you have features for each of the tiles, usually you're interested in aggregating these features. There is a variety of possibilities here in how you want to aggregate the features to obtain your slide feature. And also here we implemented different methods. And finally, what I want to stress is this pipeline is fully fine-tunable. That means you can fine-tune your encoder at training time based on your loss. And I want to remember here that we're talking about with labels. We usually have labels just for the full slide, not for each slide. Now, just a few more details of some of the functionalities you can find in the package for each of these modules. We talk about tiling. Now we implemented two different modes. One is a pre-tiling and the other is tiling on the fly. There are pros and cons of both. We found pre-tiling is really convenient to have a quick machine learning iterations because you just need to do it once. But it also limits somehow the level of experimentation because at that point the tiles are fixed, while it helps to have much more variance and, for example, have different tiles at each epoch. That means tiling on the fly. And for this, we integrated, for example, with some components from Monet, that maybe those of you that are working in the field are probably familiar with. It's a library from a different university and supported by NVIDIA, and they have a section for computational pathology. So we, and it's open source, and we really collaborate with them to integrate as much as possible tools from their library. And the other section that we have seen in the previous pipeline was about training your own encoder. Now here, I want just to stress which are the benefits of using a self-supervised learning encoder trained on histopathology dataset. For the two use cases we were looking at, we can see here the difference when we use the encoder that has been trained on the same dataset. And the improving in performance is particularly evident in the case where we don't want to fine-tune. So this is why I think you should really look into this part of the package. And I will not go into more details. I'll just point you towards the documentation that is available that describes how you can train your own encoder. Here, I want just to mention that there is the possibility to choose your model, to configure which are the augmentation you want to use, to evaluate your encoder online. This is something we found really convenient. Sometimes this runs run for a week, and you want to know if you can stop, your encoder is good enough, or you should train more, and checkpoint is already implemented, and scalability to multi-node. I'm doing with time. Good, perfect. Okay, so hoping that you still remember the pipeline image. The following step was how to aggregate features from the different tiles. Here, what we made available in the package, it's a list of different layers that can be set up in your configuration files. You can go from something really simple like min pooling or max pooling to attention layer. And we also experimented and made available transformer and pooling layers to take in account the location of the tiles. Now, probably the most interesting part at this point, how can you train your own model if you install the package? So it's actually really simple. As long as you have your environment created, you can point to the runner in the package, and all you have to do is to specify which is the name of your model class. Now, the model class, it's something that is inheriting from a class we defined. And ideally, all you have to do is to specify in this class which are the hyperparameters you want to use for your experiment. In the same class, you could, for example, also specify which are the augmentation that you want. And this is it. And just to give a bit more of detail, all the packages heavily created around PyTorch Lightning. So this configuration class is inheriting from a PyTorch Lightning container, if some of you are familiar with the tool. For more details, I think this is the best place where to start. There are examples of different configs files. You can start from there. You can take some of the configs there to reproduce those two use cases I was presenting before. And from there, you can do your modification and experiment as you wish. Now, assuming that you have been able to submit your run and it's training, in case you're training in Azure, something that you gain is a lot of monitoring of your models without having to implement your own functions to check the loss or the accuracy. So these are just an example of what you can get basically for free. Here we are tracing the accuracy, UROC, and loss for training, and for validation. We're doing a cross validation. So these are like the different lines are different folds. And for example, this was the Panda experiment I was mentioning. It's a multi-class classification. This means we were interested in also monitoring the accuracy for the different classes, and we can just get this for free. It's really convenient. The final step, let's assume that we obtained some results models. We want to, at this point, interpret the results, possibly with the help of a clinician. The solution that we implemented in the workflow so far is based on Digital Slide Archive. As I was saying before, this is open source. You can install it and you can create your own instance. What we offer in the package are some tools to basically transfer results, for example, from Azure to the DSA instance. And it's very easy, like you just need, like, for example, the run ID and the address of your DSA instance, and that's it. And what you will obtain, it's something that looks like this. So here, what we're seeing is an attention map that is saying, like, for each of those styles that we created, how much attention the model was paying to for each of these styles. And one nice thing of DSA is that you can easily zoom in, zoom out, overlying like different contours. So for example, here we are zooming in on this part of the slide, and we can look at much more detail and higher magnification at what's happening. And we found this was convenient for clinicians to understand what was happening and to get their feedback if the model was making sense, and how we could change the model, for example. And you could also like compare the results of different models, how the different attention maps looks like. I hope this was a good enough overview of the package. If you're curious about, I definitely invite you to look at the documentation that is online, and you can find here the repo and the pip installable package. And if you have any like questions or comments, please reach out. Open GitHub issues if you find problems or you just want something else implemented. In general, we're happy to hear about feedback. And I'll just close here with my main takeaway message.
Thank you for the great talk. So we have time for questions. So maybe I can start for a question. So
sure.
Thank you very much for the talk again. So in the talk, you mentioned that you offer two different family of techniques of contrastive learning, CMCLR and the bio.
Yes.
So I'm wondering if you have an intuition, because in CMCLR, you need to define enough negative examples, and it's like maintain this bank of negative examples is sometimes computationally expensive. So do you have any intuition about what is the performance between CMCLR, particularly for the pathology that is high resolution, with the bio, or how you define the negative examples?
We tried both the models.
Mm-hmm.
In our use cases, we haven't seen a huge difference.
Mm-hmm.
And usually we use CMCLR
Yeah.
as standard.
Yeah.
So that that is my intuition. Like it's an empiric intuition. Like it like it seems good enough. You're right. In any case, like how you define like the negative example is a very tricky thing, especially when working with tiles, because obviously like for example, should I take the negative example like from the same slide, from a negative slide and having like a semi-supervised approach? At the moment, what is implemented is like not making a distinction based on the label. So you have like your bag of tiles, and any tile that is not like your positive example can be a negative example. And obviously that is a limitation. Like there is much more that we could experiment with, also like in terms of maybe locality, like a closed tile, obviously maybe it's not really a negative one. We just go with the fact that the bag is like kind of large enough, and if you random sample, it's likely it will be really close, or even like belonging to the same slide if you're working with many slides.
Okay, thank you. So we have time for, yes, please.
Yeah, a few people were looking at me after the talk finished, so I thought I have to ask questions. So a couple of quick questions. First of all, well, very nice talk. Thank you so much for sharing your progress with us. So first of all, how easy, difficult it is for other researchers to contribute their models, their work to your repo. And secondly, why go back to DSA? DSA, as far as I know, is not used by any pathologists.
Okay.
Why not what the previous presenter talked about, send the results back to the pathologist workstation? There, obviously, it was being sent back to the PEG system for the radiologist to look at the results. Why not do the same for the pathologist as well?
Okay, so I'll take both the question. The first one, how is this to contribute? I have to say that we released this very recently, so we don't have external contribution at the moment. So we're curious to know. We have had external users, and the feedback was good. Like someone not belonging to our team just was able to start running and training their own model, and just a few days looking at the documentation and following the instructions. So for me, that's a good sign. Obviously, like contributing might be a bit more difficult. It also depends, like if you want to suggest a new configuration file, for example, because like you use this package and you have your paper and you want to say, these are like the set of hyperparameters I use. I expect that to be really easy. If you want to do some major changes to the design of the package, obviously that would be more difficult. The second question is like, why don't sending that back to a pathology station? Well, I have to say this has been developed really at the moment for research, not for clinical implementation. I can see easily that in the future, but we're not at that stage for computational pathology. This is why this was the tool we knew about, that we had tried and seemed to work fine, and it was completely open source. I would say the implementation is really agnostic. So if someone has another favorite platform to visualize slides, that could be very easily extended. And this is also the idea that we had in mind. Let's start with this one that is open source and used enough. And after we'll see if there is the need to integrate also to more platforms.
Thank you.
Yes.
Okay, thank you for the great time. I've got two questions. So first is, so I saw that you did like most of the design of the tool is based on MIL. I wonder if there is a chance for you to include whole slide level segmentation models as well, so because they need also some special considerations for segmentation tasks, which are required for many applications in computational pathology. And also have I wonder if there is, so because you're working with Azure and Microsoft, if there's already like a repository of TCG images available through Azure. So people want to download them and upload them again, so just quickly access them.
Okay, thanks. I think these are both two good questions. How easy will be to include segmentation? I have to say that, yeah, the pipeline we developed so far was really focused on classification. That are the type of downstream tasks we focus on. A lot of extensions can be made. So possibly, but it's not like an immediate extension for sure. The other question was about like, are these datasets already available on Azure? No, we don't about it. Hosting the datasets. I think Anna here can comment on this. Might be not the easiest thing for Microsoft to do because we don't. I mean, we're not the managers of those data. It's public data and it's personal data. So probably Microsoft doesn't want to be the host. What we have done to facilitate the user as much as possible, as part of the documentation, also to include quite a lengthy description of how to download, for example, from TCGA, so that there is already like a to-do list on how you can recreate your own data set. And for example, TCGA CRCK, it's already available also on Zenodo, already pre-tiled. So it's really easy to obtain.
Sorry that I interrupt. Can we move questions afterwards? We need to move to the next talk. Sorry for that.
We can chat after.
Yeah, thank you very
Thank
much.
you very much.
So should we aim to finish at 22 then, is it? Is it the,
Yeah, that's okay. Yes. Yeah.
Okay, so we're gonna get started. So yeah, that's gonna be a bit different from the compute power and the engineering prowess of Microsoft Teams. Here we're going to talk about a small startup in Cambridge, just next door. I mean, the headquarters are next door to Microsoft, but slightly different company. And hopefully it's going to be a useful story about the kind of things where machine learning for histopathology can fit. So the company is called Cited, and yeah, we do a number of things, but the mission, the one we want to emphasize, is about esophageal cancer. And the early detection, the early diagnosis of that. So yeah, four points, and mostly it's going to be storytelling about the company, giving you some background. There's going to be point 3 about machine learning. It's going to be quite short, not very technical, hopefully very digestible before dinner. So let's start from esophageal cancer and its early stages. So esophageal cancer is in terms of the impact in terms of deaths, apparently the sixth most impactful cancer. And in the UK alone, the figures I have is it affects 10,000 people per annum. Globally, of course, it's in the hundreds of thousands. Now, there's a number of stages in the development of towards esophageal cancer. And in particular, we are focusing in the early stages on what's called Barrett esophagus. So Barrett esophagus usually comes from people who have some early symptoms, which are gastroesophageal reflux disease, GERD or GORD. And then Barrett may develop into dysplasia, low grade or high grade, and ultimately cancer. That's the mostly Western scenario. That's the most common type of esophageal cancer, mostly prevalent in the West, which is an adenocarcinoma. By the way, if we look at Barrett esophagus, I don't know if you can see that. The way you can see that if you look with the endoscopy is that usually the lining, the healthy lining of the esophagus should be kind of whitish or very, very light pink. And at some point, if you reach the junction to the stomach, Barrett is evidenced by some red things appearing starting from the junction and growing, and quite visibly growing quite high here. And that's because the epithelium is mutating, maybe not the word, sorry for that, from what it should be normally, which is some squamous epithelium, to some epithelium which is close to the gastric type, which is actually which looks like the intestinal type. So it's useful to think about the incidence of these various stages. So GORD is actually quite widespread as a problem, over 5 million people. Barrett esophagus is very under detected. So it's conjectured that in the UK, it would be probably over 1 million, probably 1.5 million people. The number diagnosed is 10% of that. So it's a vastly underdiagnosed problem, we believe. And if we think about the survival, well, the conclusion is that you really want to detect these things early. Survival, of course, at the late stage of esophageal cancer is poor. Early detection allows a number of actions. For instance, you can do surveillance, if needed, do ablation, and a number of things. So I don't need to convince this audience that detecting early is good. Now, how do you detect early something in the esophagus? So you have to look there, you have to send the camera, it's called an endoscopy. There are some limitations to endoscopy which make it not suited for large-scale screening programs of the type that would be needed in the UK and in the West and in the world. Endoscopy is good for when you want to precisely measure, for instance, the length, the so-called Prague scoring, for instance, of Barrett and things like that, when you want to do, well, biopsy, taking a biopsy, taking a sample, doing an ablation. But in terms of scaling to what we want, there are too many limitations. It's too invasive, and for this reason, there is no screening program in the UK or elsewhere. Now, Cited exists because there has been this innovation coming from Cambridge University, developed over 15 years, where there is now lots of clinical evidence, which is an alternative way to do screening, which is called cytosponge. In contrast to endoscopy, it's a nurse-led office-based clinic, something that we hope that will be suitable for primary care, and it's something we are trying to investigate. Much shorter appointments, much less invasive. So hopefully the kind of thing that would be appropriate for large scale, for widespread screening. So I have a video of how cytosponge works. The beauty is it's very low key. It's a sponge on a string in a capsule. You swallow it, the capsule dissolves, it releases a sponge. I'm told it takes 7 minutes. I still haven't tried to do it. I'm planning to do that. You pull it out. It's not pleasant, but it's not quite an endoscopy. People report it's usually a very not too inconvenient test, and you can see that it scrapes, it collects samples all across the lining of the esophagus, starting from the stomach. So that's the context. That's what Barrett. That's why Barrett detection is important, and what we want to do at Cited. Now, what do we do with the cytosponge samples with when people collect the sponge? How do we translate that into a diagnostic? So Cited as a company has a lab and processes end-to-end from receiving the sponge to producing a diagnostic sent to NHS or things like that. And what we do in between is a number of steps of collecting, so taking the sponge, passing it to a centrifuge, obtaining a block, and then slicing. And what we obtain is really normal, what you would expect from histopathology samples, with just some kind of oddities. I mean, they are not the kind of tissue you would find from biopsies. Obviously, it's kind of samples projected with bits of gastrocolumnar epithelium and other stuff onto the samples. And usually we have these typical things where we have 2 slices per actual whole slide image, and we use a number of biomarkers. So we use the classical H&E marker, which is good for morphology, always the one that the pathologists start to look at. But we also have some specialized markers. So TFF3 is good for revealing metaplasia, which is something which highlights essentially Barrett. And P53 is one which is useful for revealing the more advanced stages of dysplasia and cancer. Actually, I'm not sure which one of these because I haven't looked at P53 yet. So that's how we translate things into images, and this is the stage where I start to get more familiar with things. The TFF3 and the P53 slides you could see underneath were actually completely negative in my understanding. So there was not much to see there. But if you see examples where there is something positive, this is the kind of highlight you would see of like a bit where there is TFF3 positive and P53 positive, unfortunately, for these patients. So it's quite complex what happens at site edge. It's entirely processed by humans. I mean, it's behind the scenes, of course, it's always more complex than you would imagine. This is a part of the workflow that a very small part of our workflow that has been mapped by our product team. So this is specifically the kind of things that the pathologists go through when they inspect a sample. There's tons of stuff going on. Obviously, before that, with lots of issues of doing that in a way which is ISO compliant and all the good practices, of course. It is one thing I want to highlight, which is that we just reached a stage where we have processed 10,000 cases. So we delivered as a company since we exist in 2 years diagnostic for 10,000 patients, which was the achievement of last week, which is great to have. Right. So notice that in the process I described, there is no machine learning. So as a company, we started before I joined, the company started in a way that actually doesn't overthink the place of machine learning, start by getting a process that actually works. And I think it's a good place to be, because then we know what we are automating, we collect data, we have lots of insights, and now is a good time to start thinking about putting the machine learning. And the goal of what we are trying to do with machine learning is to of course, to bring some scalability, so to remove from pathologists the weight of all of the easy cases where they are simple enough to be processed by a machine. And essentially, the approach we are following is something that the founder of the company is the first author, did a proof of concept of in his PhD. So as part of his work in Cambridge, he essentially showcased, did a proof of concept that you could do a triage-based approach where you could considerably remove, scale up the work of pathologists. And there's a number of steps to that and a number of machine learning tools that we have to develop. One of them is the first part on top of that is to verify the quality of the samples. There is a problem where the samples don't reach the stomach and you have to reject them because you can't really assess that there is no Barrett if you haven't reached the actual stomach. And then there is the actual grading of metaplasia, where you say yes or no to whether the patient has Barrett. So just a few words about each of these aspects. Quality control is the one which, to be honest, we are focusing on until the end of 2022. It seems to be like a simple case, but this is an ambitious enough task for the size of this team. It looks like that on H&E. So what you see highlighted is delineations of bits of gastrocolumnar epithelium, and in the actual giant image, you would see bits of these in various places. So the goal is to quantify whether there is enough to be confident that the sponge has reached the stomach. And from the paper, these are not the data that we have recently, but from the paper, the idea about how we are confident or confident that there is enough, or that there is enough, or that we are maybe not confident in the middle, is based purely on quantifying the number of tiles or the number of square micrometers, something like that, of gastrocolumnar epithelium. So that's part number one. That's the first component that we are in the process of developing and hoping to deliver by end of the year. Part two is going to be Barrett diagnosis. So here we see actually in H&E, this is the way things look. So the blue goblets, which maybe I should point to, but you would see some blue here, which is, yeah. So this is all gastrocolumnar, columnar epithelium, and this is what things look like when there is metaplasia, which is also revealed by the TFF3. But you can also see it just on the H&E in some cases. So that's the kind of things that the paper also shows we can automate. And same things, there is this consideration of finding a sweet spot where we are very confident and can deliver a verdict where we don't need a pathologist, or when things are positive or negative. But also the model should be very clear about quantifying its uncertainty and knowing when it's in the I don't know zone where we resort to screening with an expert. So that's the idea. So how do we do that? Well, there's nothing very original to the approach. I mean, this is the kind of slide that highlights the software, the machine learning model we are doing at a very high level, where we are breaking things into tiles and we aggregate things. We actually don't plan to do multiple instance learning at this stage or things like that. It's purely a counting exercise for at least for the quality control thing. So we just need to be able to quantify the number of tiles which are positive for coronary epithelium, or maybe to actually have a nuance of that where we quantify the certainty or the surface. Maybe there's a number of variants we can play with to assess the overall sufficiency of the sample. The idea is that basically the same kind of software we are developing is going to be, I mean, the framework we are developing and which we aim to have to pass ultimately CE marking is going to be common to what we do for both of the stages, because there's lots of commonality there. So that's pretty much what I have. Now a number of maybe of discussion points which I can't read. What did we learn? So I joined this company less than 6 months ago. So in a sense, we are still early in our development. One of the observations perhaps is, like you might say, is just re-implementing the paper from Natural Medicine 2021. I think it's true, and I think it's actually a good thing, because we don't want to break new ground. We want to ship this thing. We want to deliver a diagnostic to lots of people. So research will come later, but for now it's good to actually start by something that has lots of clinical evidence and where we are not in unknown territory. Now, having said that, as some of you might know, there's a difference between code in a paper and making that actually pass certification and integrating into the software stack. So it's not like there is no work to do before we ship this thing, but we are confident that we kind of know where we want to go. Like I said, yeah, our big focus is going to be not short term, but probably towards 2024 or 5 to actually have this thing CE marked. And software as a medical device. So this impacts the way we take our decisions now. It's about how we can get there in a number of years. It's going to be a long journey. And of course, it impacts both our software development and the evaluation. So just last week, I was writing a long document about the number of things we want to verify long-term about our model. Do we quantify our uncertainty well? Do we generalize other changes of stains, things like that? Like I mentioned, yeah, as a startup, it's interesting, well, for me, to think that we actually were not created ML first. I mean, some startups start from the ML and then sometimes struggle to actually define their problem, whereas I think in our case, we started from the problem and we got it to work. And now it's kind of a good position because we have lots of data, we have delivered something already. The data can help us, of course, build our confidence in the model and do our evaluation. So it's a good place to be. We also have pathologists to talk to who know what they are doing when they are annotating stuff for us. We are just in the middle of a wave of annotations for feeding more data to our quality control model. There's a number of small technical points which are perhaps unsurprising. I mean, we expect uncertainty calibration to be a crucial aspect of what we are doing, because we really want to find this zone where we can very confidently say yes or no. And it's okay if there is something in between where we call a human. The human is not going to disappear, but we want to be really, really certain when we say no Barrett automatically, for instance. Yeah, we are worried about staining sensitivity. We cannot control end-to-end everything in the lab. It's not like we have third-party providers, so we cannot control that, but still there is still within the lab some staining and some process variability as well. So this is the kind of things that we are going to monitor very obsessively. And I did mention that for Barrett diagnosis, you can use TFF3 or you can use H&E. My preference would be to use H&E. The proven path is to use TFF3. TFF3 has a cost of £35 per sample. So overall, if we want to deliver this diagnostic cheaply at scale for NHS and other people, these things matter. But yeah, there's a number of open questions on the way we're going to have to provide a bit of new science. So that's it from me, and here is the team.
Thank you very much for the great talk. So we have time for one or two quick questions. Yeah, please.
Thank you. Very interesting. Just in terms of the esophagus, so when you get the sponge, do you get everything? Because in Barrett's, it's normally localized on one side or another side. So if the esophagus is elongated and the sponge gets not through the parts of Barrett's, you wouldn't get the tissue of Barrett's.
I don't know. I mean, so I think the evidence is that we collect enough, I think, which is the point. But yeah, I think there are all of these very subtle issues. It does get, there are lots of subtleties about, yeah, knowing that what we have collected Barrett, that there is enough sampling done. So one of the subtleties, for instance, is we do have to reach the stomach. How do we know that? So we have to have gastrocolumnar epithelium. But we have to distinguish that from the columnar epithelium that would be Barrett, which is very subtly different. So lots of things like that. And this is where all the science done in Cambridge is the proof of the pudding. Like so Professor Rebecca Fitzgerald is the authority, and her group are the authority on that. And they have studied these questions, and the science is that it works as a screening device. But yeah, there are all these subtleties like.
Thank you. Okay. Any other questions? So a very quick, curious. Yeah, we have. Okay.
Sorry, I have a quick question. Like, for the image, like, do you have the annotation for each pixels, or because you're using the tails to make the prediction, right? So, like, how about how you define, is that a negative or a positive?
So is your question about how we train this thing? For instance, what annotations we collect?
Yeah, is that for the like object-wise or pixel-wise?
So we do have to work with pathologists, and Cambridge has done some of that. So some of the data sets we use actually are reused from, or both are acquired from cancer research and Cambridge. We are also doing our own internally, where we pay our pathologists specifically to the annotation. It is really about delineating finely, for instance, at a fairly high level, well, ultimately at the finest level of zooming, where within some areas, which we agree on, there is, let's say, columnar epithelium, but there's lots of other stuff as well in these images. So yeah, it's a tedious, as you imagine, it's the usual thing. It's a tedious, costly process, but we luckily, because we have people that are working on that 10 hours a week or more, they know what they are doing, and we can just pay them.
Yeah, thank you.
Yeah. Okay, thank you. For sake of time, please, let's thank again the speakers. You want to?
So next activity will be our gala dinner. So the gala dinner will be 7 p.m. today, but the door will open at 6:45. So we got some time to look around, enjoy yourself. And the walking distance from here to there is about 20 minutes. Okay, you can just Google, Microsoft here, we should say Bing Maps to search Trinity Hall. Okay, so yeah, Trinity Hall is the place. And you can collect your tickets upstairs from Claire. Yeah, it's something, something looks like this. So you need to collect the tickets to get in. Okay.
Yes, please collect your ticket that in reception, please.
quickly talk to you. My name is Guang, so I'm the organizer of this conference, and you're from Microsoft, right?
Yes.
Yeah,
correct.
nice to meet you. Nice to see you. Yeah, it's really blunt, and the thing is, we also organize this conference for the BMWC, so it will be in
Sorry,
November.
BMVC.
Well, BMWC, which is like a machine vision. So we got like a sponsor normally from Microsoft as well, but the guy like already left Microsoft, like my colleague told me. So we just want to make some contact with some people from Microsoft.
Probably, probably keep in touch with my friendship together.
Oh yeah, okay. I know him. Yeah, I know him, but he will not join us today. He have collected.
Yes, there was something happening. Yes, but can we probably
Okay. Sure. Okay, that's great. That's good. So you're coming today.
Yeah.